In many situations, soils are loaded under zero-lateral strain condition. For example, during burial, so let's say that this element just deposited, and now successive layers are going to come to the top, and so this element is trying to contract and get shorter and fatter. However, all the other neighbors are trying to do the same. Therefore, there can be no lateral strain. However, there will be vertical contraction. The same happens if you place a very large footing on top of the surface, which is much larger than the depth of burial of that element. It will create a similar situation of a zero-lateral strain loading. So the question for us is, how will the state of stress evolve in that element, but also how will the density of the element, the void ratio, the unit weight increase as burial increases? Of course, we can anticipate that the higher the state of stress, the higher the strains in the vertical direction. However, the strains are going to become increasingly smaller because the soil is getting stiffer and stiffer. So this is the true behavior that we anticipate, even though this is not the way we typically present in our geotechnical classes. Therefore, today, I would like to explore this in more detail. And the situation starts as follows. If we take a subsurface and we observe how the pressure increases with depth, then we have to take a slice here, let's say of a thickness dz, and we are going to compare what is the stress or the pressure acting at the top with the stress or the pressure acting from the bottom. This is our starting point. So let's write that equation, and for the first case, we're going to explore this situation in the case of water. Then we're going to look up into the atmosphere and consider gases. Finally, we are going to come back to soils with a renewed understanding of what is going on in soils. So let's start with case 1, which is the case of water. If we write the equilibrium conditions for that case, from the bottom, we're going to see that there is a pressure, U, which is the value of the pressure at the top plus the gradient of the pressure with respect to Z multiplied times dz. This is the gradient, therefore this is the increment. From the top, we have uz, and to complete the force equilibrium is the weight per unit area of this very thin slice. So let's write that equation of equilibrium. It's going to be uz plus the gradient of u with respect to z times dz is going to be equal to the pressure from the top, uz, plus the unit weight of water times dz. All this is, of course, per unit area. And now we can simplify, and what we get is that the gradient is equal to the unit weight. Now, if the unit weight is constant, for the case of water that is approximately correct, then the pressure increases with depth as uz is going to be equal gamma water z plus a constant, and we solve for the constant when z is equal to 0, and when z is equal to 0, we could either put the atmospheric pressure. For most problems, then it becomes on both sides of the equation, and we can automatically remove the atmospheric pressure. Therefore, we keep that equation for the case of water. And so, indeed, in a swimming pool, when we have water in a swimming pool, the pressure increases linearly with depth, where the gradient is the unit weight of water. Now, the question becomes, more interesting if we think in terms of air. So now it's going to be a similar formulation, but the story becomes a little bit more interesting. First of all, we have to see the problem upside down. So the pressure at a higher elevation is going to be lower than the pressure at the lower elevation because of the unit weight of the slice. So we are going to have Z going upwards, and the equation becomes UZ plus the gradient of U, now is the pressure in the air, dZ is going to be equal to the pressure at a lower elevation, UZ, minus the weight of the slice that is pushing down, which is gamma air times dZ. And yes, we can simplify that, but there is a problem here that the unit weight of air is very sensitive to pressure. As you may remember, pressure times volume, so we are going to say UV equal constant, and we have used the letter U, but in case of air, we tend to hear the Boyle-Marriott's law as PV equal constant. So U is the equivalent of P in this case. Now, if we divide both ways by a certain mass in that slice, the mass will remain constant. However, it's going to occupy a smaller and a smaller volume. So this is the mass density. If I multiply times G, which is another constant, this is the unit weight. And so we bring the inverse of the unit weight. So if we bring it to the other side, then this is going to tell me that the unit weight of air is equal to a constant, let's say A, times the pressure of air, and this is at depth Z. By the way, we can solve for the constant of A right away, because we know that the unit weight of air on the Earth's surface is about 12.2 newtons per cubic meter. This is the unit weight of air at 1 atmosphere, which is at a pressure of 100 kilopascals. Therefore, A is this ratio, which is 12.2 newtons per meter cubed divided 100 kilopascals, which is 12 over 100 per meter. But the important thing is that this equation now is a linear equation. It's surprising, but unit weight increases quasi-linearly with pressure. And so if we replace in this equation du dz dz is equal to minus gamma A dz, we can also cancel the dz, and this is equal to minus the factor A times u. So we have a first order differential equation, and the solution for that, what we're looking for is something that a function of u versus depth that will appear both on the right and on the left in the same form, so they cancel out. And what is a function that its derivative is the function itself, is it's an exponential. So if we say that u changes with depth as a value at the origin times e to the minus alpha z, and we plug it into this equation, then we are going to get that on the left, we are going to get minus alpha times the function is equal to minus a times u. Let's write it down. u0 e to the minus alpha z, and here once again we have u0 times e to the minus alpha z. Therefore, this cancels out, and we have that A is equal to minus alpha. So the solution for the pressure of air in the atmosphere is equal to the pressure at zero elevation, which means at the sea level, u0, times e to the minus alpha, where alpha is equal to A, and A is equal to gamma air at 1 atmosphere times Z. Or we could have placed 100 kilopascals. As a matter of fact, this equation fits quite well the data for atmospheric pressure versus elevation. The higher we go, the lower the atmospheric pressure, because the burial of the atmosphere, it gets lower and lower, and therefore the weight gets lighter and lighter. For example, when we go up in an airplane, the pressure decreases, and in order for us to keep some comfort, they maintain some of the pressure. They're actually depressurizing the airplane, but not as much as the external pressure. So for example, if you take a plastic bag with a little air, it will become inflated during takeoff because the pressure in the airplane is decreasing. However, they do maintain a significant percentage of the pressure that was on Earth for our own comfort. So now we have to wonder, what is the pressure or the effective stress versus depth as we go deeper and deeper into a soil mass? In the case of soils, we start with the same equilibrium equation where the overburden keeps increasing with depth, and at a given depth z, we can make an equilibrium analysis between the stress from the top and the stress at the bottom. So is the gradient of the effective stress with z times dz, that is the increment across that very differentially thin slice, is going to be equal by equilibrium to the effective stress at the top plus the weight of that slice, which is going to be the weight of the soil, but this is the actual weight acting on the skeleton, and therefore we're going to say that this system is dry for this exercise, and we can certainly generalize it for when there is water, and this is gamma dry times dz. Now we see some of the cancellations taking place as well. Now the question is, what is gamma dry? Gamma dry is equal to the weight of minerals over the volume total, and the weight of mineral is equal to the volume, is the same as here, is unit weight is weight over volume, therefore weight is unit weight times volume. So this is the volume of minerals times the unit weight of the minerals, which we can replace by the specific gravity times gamma water, and this is the volume total, is the volume of minerals plus the volume of voids. Therefore, the dry unit weight of a soil is equal to, divided both numerators and denominators by volume mineral, is gamma mineral divided 1 plus void ratio, which is, as we said earlier, specific gravity times gamma water over 1 plus void ratio. And so now we can replace here, and the gradient in the effective stress in the direction z dz is going to be equal to gamma dry, which is the specific gravity times gamma water divided by 1 plus E at depth z. And that is, now we go back to a situation which is identical to what we saw in air, that the unit weight of air changes with pressure. The same here, the void ratio of the soil increases with effective stress. And if we see the typical behavior of a soil in the true axis, this is void ratio divided by versus effective stress, and this is the true behavior. It starts at the void ratio that corresponds to the asymptotic value to 0 effective stress, and it decreases, and it goes pretty much to 0, for example, in shales. However, we got used to the history of our field of plotting this in semi-log scale, which has some advantages, but be careful, there are some disadvantages as well. And when we plot in a semi-log scale, we see the trend behaves something like this. This is void ratio in the logarithm of effective stress Z. Furthermore, what we have done in the field is we tend to feed this part with one slope and this other part with another equivalent linear system. And all this was very useful at the time when, in the 30s and the 40s, where calculations were done by hand without a calculation, without a computer, and everything was plotted in either linear scale, linear log, or log. By the way, we look at the slope of one of these equations. So the delta E over the delta of the log of sigmas is the log of the ratio. So this is the delta of the log of sigma high divided log sigma low. And then this becomes equal to delta E over the log of sigma high over sigma low, where this is sigma low plus delta sigma. For clarity, we should normalize this by kPa, and this one also by kPa, but that cancels out in the ratio of the logs. And this is, for example, in this regime, let's say that we call this C sub C. This has been the tradition in our field, and I think that we have to begin using continuous functions, which are versatile, do not give us the inconvenience of figuring out what sigma p prime is, and curve fitting errors, and there is no derivative at the intersection point, which creates numerical instabilities. So let me write a couple of asymptotically correct equations. And that is very important when we want to have something robust. It has to be asymptotically correct in the sense that as the stress goes to 0, we don't see that in logarithmic scale, we certainly see it here. As the stress goes to 0, the void ratio goes to an asymptotic value we are going to call E0. And as the stress goes to infinite, the void ratio is going to go to another asymptotic value, E infinite. And so what are some possible functions? For example, one is a power function that looks as follows. The other one that works very well is an exponential function in which E, and we should say E at the depth Z or as a function of sigma Z, is equal once again to the asymptotic void ratio minus the change in void ratio from at the asymptotic conditions to the other one is 0 minus E infinite. But now we distribute this change in void ratio from the two asymptotes with an exponential function times 1 minus. So folks, these are continuous functions, and they will fit the data from the very low effective stresses in linear scale going to 0 effective stress to very high effective stresses, which are relevant not only for the engineering regime, but also for sedimentary basins and for petroleum production and CO2 storage, etc. So we had concluded that the gradient in effective stress with Z is going to be equal to the unit weight of the dry soil, and that one is a function of the effective stress. So in order to solve this equation, we may be able to find a closed form solution. In fact, there exists a closed form solution for the case of the exponential void ratio with an exponent of 0.33. Otherwise, you have to do the integration numerically, and of course it's very simple. You start at a depth Z equal to 0, and you know the effective stress is 0, and the void ratio is E0, which is the asymptotic void ratio here at the origin. And based on that, you can compute with the equation that relates void ratio to dry unit weight, you compute the unit weight. Now, that unit weight is for the slice which is very much at the top, which is going to apply the load on the next one. So if we increase here by delta Z, now you have a new value, and this unit weight adds to the effective stress above times dZ it will add to increase the stress, higher void ratio, higher density, etc., and you integrate to any depth desired. So we're going to effectively do it numerically, and yes, there are ways to improve the algorithm I have just described. Clearly, now we can anticipate what is the evolution, not only of effective stress, but also void ratio with depth. It could be underneath the footing, but we can also do it for sedimentary basins. And you may remember from earlier presentations that the void ratio, the asymptotic void ratio, was dependent on the soil-specific surface and other characteristics of the soil. So that's a parameter that you will need to know, or that you will measure, or you can extract from those charts. The other parameters we are going to see how to determine. But there are different functions. They have this form with different components. Here could be the exponential, power, hyperbolic. We are going to include a series of very robust functions, very reliable functions at the end of this presentation. Please take a look. Using those functions and those asymptotic void ratios, we were able to predict the evolution of effective stress and void ratio with depth under a wide range of situations. We are going to include those as well at the end of this video. Finally, you may be wondering, how is the horizontal effective stress increasing? And the fact that it's zero lateral strain means that the soil is getting shorter, trying to get fatter, but it can't because the neighbor is doing the same and is pushing back. So the stress is actually increasing, the horizontal stress. And in this case, we really don't have a very theoretical formulation. We go back to the fundamental empirical equation, let's say by Jackie, who says that the ratio of horizontal effective stress to vertical effective stress, by definition, we're going to call it K0. So this is a definition. And please, it's very important to realize that this is ratio of effective stresses. It cannot be total stress because the water is doing one thing. According to Pascal, the horizontal and the vertical pressure in water is equal to 1. However, the granular skeleton, because it's frictional, is doing something else, which is what K0 explains. And this is Jackie's insight. If you look at his data, the original data is pretty much between 0.4 and 0.55. But if you he actually proposed the following equation. K0 is going to be empirical, 1 minus sine phi. And that is a nice intuitive expression, because the more frictional the soil is, the less its tendency to push sideways. In fact, if you think of water with no friction, this ratio for water becomes 1, where friction is 0. So the asymptote makes sense. Now that is for a soil that is not preloaded. If the soil has been preloaded, now it will lock in some of that effective stress, and so K0 for a preloaded soil is going to be also empirical. It's going to be proportional to the K0 not preloaded, the virgin K0, times the preload ratio, which in clays we tend to call it the overconsolidation ratio. However, this is totally applicable for sands as well, to the sine phi. And for this one, you can look at a classical paper by Main and Kalhawi, 1982, where you will see how all these stresses are evolving during loading, unloading, and reloading. I will include that reference in the suggested readings at the end of this section. But let's put some numbers. Let's say that friction angle is 30 degrees. It's going to be higher for most soils, particularly coarse soils, but because for simplicity of the calculation, that means that sine phi is 0.5. 1 minus sine phi is 0.5, So K naught not preloaded is about 0.5, which is basically the data that Jackie had. Now, what happens if there has been a preload ratio of 4? So the soil currently experiences a load 4 times lower than the past experienced load. 4 to 0.5 is 2. Square root of 4 is 2. 2 times 0.5 is 1. And so the K naught preloaded now is 1. So the horizontal stresses are quite high. In fact, it could be significantly higher, reaching the asymptotic stress of anisotropy in a soil, which we will discover in future presentations. So now to complete this story, you can go back here and not only compute sigma z, but you can also compute sigma horizontal effective as K naught of the sigma vertical, but please be aware of the loading history, which may have caused preloading, and the actual stress ratio may be higher than 1 minus sin phi.